Let's go ahead and start passing out homework. Austin Martin. Brandon Simpson. Hey, does this look familiar to you? Does this look familiar to you? Okay, Brandon Simpson? No. Tyler Koshaway. Michael DeBach. Anthony Lee. Jesus Rodriguez. Jacob Childers. Carlos Aguilar. Hey, this wouldn't be yours? Nope, okay. Jory Owens. Yeah. Thank you. Val Peterson.
Here.
Carter Dewberry. Chris Macklin. Megan Walker. John Coldwell. Oh man, somebody tear a sheet of paper out of your notebook and pass it around for people to sign in on. You take care of that, Val?
No.
All right, thank you. Jacob Huffman.
Here.
Travis Black. Jimmy Flood. Flood. Deja McClellan. Go. Matt Letney. Jacob Sanchez. Did someone? Jacob Sanchez? Nope. Matt Letney. Jacob Sanchez. Tyler Koshaway. Brandon Simpson. Oh, I think I've got another one for you in here. Yep. Here you go, Brandon. Carter Dewberry. Stephen Turner. Anthony Lee. Okay, let me see. I think I got Okay. Zach Woodard. Hey. Zach Woodard. Jacob Huffman.
Yeah.
Stephen Turner. Huh. Yeah. Anthony Lee, Jacob Huffman. Zach W. Pardon me. You Megan? Yeah. Okay. I got some up here for you. Jory Owens. Man, you people make me walk a lot. Jacob Hoffman. Okay. Jory Owens. Tricked you. And Zach Woodard. Stephen Turner. Anthony Lee. Did someone just say here to Anthony Lee? All right. Tyler Koshaway is still not here. Chris Macklin is still not here. Chris Macklin, they came in. Hoorah. Here we go. Megan Walker is here now. Travis Black. Matt Lutney. Jacob Sanchez. Carter Dewberry. Still hasn't come in. Okay, well, that covers it. All right. And one more time, does anybody recognize this? All right, well, at some point, somebody's going to claim some points. But go ahead and turn to chapter 2.4. We're going to start looking at graphs of some of these trigonometric functions today. We're going to start by looking at the graph of the sine function, y equals sine of x. Okay. If you'll remember the unit circle, you'll remember that sine of x is the y-coordinate of the point. Really shouldn't be x, should it? He should have used sine of some other letter, but the sine function gives you the y-coordinate. The x function gives you the cosine function gives you the x-coordinate of the point on the unit circle. And we remember that at 0 degrees, the sine was, anybody? 0. So at 0, at x equals 0, sine of x is 0. At, what was it, pi over 4? Yeah. What's the value of, at pi over 4, what's the value of sine? 1/2, isn't it? No, that's 30. Doesn't matter. Moving on, at pi over 2, we know that it's 1. The value of sine at pi over 2 is 1. What are some of these others? Oh, at pi over 6, at 30 degrees, it's 1/2. We keep on, we're going on around the circle, we get to pi. Sine is back down to 0. Pi over 2, it's all the way down to 1. And at 2 pi, it's back up to 0. If we draw a line to plot all of these points, we end up with a function that looks like this. And of course, it continues to go that direction. And in that direction. That's what the graph of sine of x looks like. But what's the range of this function? -1 to 1, inclusive. All right? But we also know we can scale the sine function by multiplying it by a scalar coefficient. So if we multiply the sine of function by some value, r, then we can scale this. If we plotted, say, y of sine of x equals, or y equals 2 sine of x, well, then this same plot, where it's at 0, it's still going to be 0, because 2 times 0 is still 0. But at pi over 2, sine of x is going to be 1, and 1 times 2 is going to be 2, so it's going to scale like so. But what if we wanted to change the period? How would we change? What if we wanted to stretch it or compress it horizontally in x? How about if we do this? How about if we plot y as a sine of omega x? That's an omega, not a w. Does anybody remember when we introduced the omega, the standard omega function earlier? Where we defined omega as the angle divided by time, made it an angular frequency. Well, that's how we scale it. What if we wanted to plot a function that's, let me clean this up a bit before we get started. What if we wanted to plot y is equal to sine of 2x? What's the period now? We know the period, if we just plot sine of x, the period is going to be 2 pi. Well, what's the period now if we plot sine is the sine of 2 times x, where 2 is now our angular frequency. The period of the function is 2 pi divided by omega. Put this in your notes. Period of the function, when you start talking about plotting a function of sine, plotting the function as sine of omega x, the period of that function is going to be 2 pi divided by omega. So you were right, you divide by something. Let's take this one step at a time. If sine of pi over 2 is 1, but what if we're plotting 2 times pi over 2? What is sine of 2 times pi over 2, or pi? 0. So sine at x equals at x equals pi over 2, then we're plotting sine of 2 times pi over 2, which would be the sine of pi, or 0. Does everyone see how that happened? We took the sine value from here and moved it back because we're now plotting the sine at twice x for every value of x. So at pi, sine of 2 times x equals the sine of 2 times pi, which is, again, 0. Well, where would we get sine equal to 1? I'm sorry, not sine, but where would the function sine of 2 times x, where would that be 1? It would be 1 when 2 times x equals pi over 2. And that would happen when x equals pi over 4. So we come in the middle here, and now we plot here, and at 3 pi over 4, we would have negative x. So now our function has half the period that it used to have. Now the function's period is 2 pi divided by omega. In this case, omega is 2. So the period of this function, 2 pi divided by omega, is pi. Now, is this clicking? Does everyone understand how changing the function with an angular frequency changes the period? If it seems a bit confusing, it actually makes it very simple once you understand this definition. Let's say we want to plot a function plot a function this time, sine of 3/2 x. What's the period? Two pi divided by omega. What's omega in this case? 3/2. So we divide 2 pi by 3 over 2. And that gives us 4/3 pi. That's our period. So we've got 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. That's the whole period. 4/3 pi over 2 is what? Be 4 pi over 6? 2, 4, that would be right here. 4 pi over 6 or 2/3 pi. Am I doing that right? Somebody help me with the arithmetic. That would be the midpoint of our period, where sine again would be 0. 1/3 pi, sine is 1, sine is -1, and we've just plotted the function of sine of 3/2 x. Anybody have any questions yet? No questions. Everybody's good up to now. All right. Does everyone see how this would work the same exact way with cosine if we were plotting cosine of x? Cosine of x starts at 1. Here, I'm going to change colors. Cosine at 0 is 1. At pi over 2, it becomes 0. At pi, it's 1 again, minus 1. At 3 pi over 2, it's 0, and at 2 pi, it's back to 1. Well, the same thing the same way we can manipulate the sine function, we can also manipulate the cosine function. So we could plot a scalar times the cosine function, Would simply increase the magnitude, the amplitude of the function. We can multiply x by some angular frequency omega to change the period of the function. Let's getting a lot of blank stares. Let's clean all this off and just work an example. Let's see if they give us one in the book here. Yeah, they do a few of them. All right, let's all right. What function do we want to map out? We're going to graph a function, and we're going to do it with key points. Okay, this is how your book describes it in your homework. It's saying graph it with key points. This is what they're telling you to do. Let's start simple. We're just going to do sine of x. What are the key points for sine of x? Where do we know the value right offhand without having to break out a calculator or look it up? Speak up. Origin. Sine of 0 is 0. We know what sine at pi over 2 is, plus 1. Sine at pi is 0. Sine of 3 pi over 2, negative 1. And sine of 2 pi back to 0. Just fill in the graph. And if you're a better artist than I am, you can probably make it look a lot better than that. That's plotting one period by key points. If they told you to plot 3 periods, you could immediately come back, fill in this one. There's your 2 periods. Add a 3rd period. Keep going out. However many periods they tell you to plot by key points, this is what they're talking about. You know where it's going to be 0, you know where it's going to be 1. Mark those 4 points. Fill in your graph. Now, in this case, what's the amplitude of this function? Oh, how many of you are in the electrical or electronics programs? Okay, for your benefit, when the book says amplitude, they're talking 0 to peak. okay? Not peak to peak. Everybody else, that may or may not mean anything, but for the electrical people, it's amplitude is from 0 to the peak of the wave. So what's the amplitude of this function? 1, right here. 1 times sine of x. What's omega? What is the angular frequency of this? It's 1. 1 radian per second. That means tau, the period, is, what's the period of this function? Omega is 1. The period, tau, is 2 pi divided by omega. So the period is 2 pi. Now, let's do a trickier one. What if the book tells you, what if the assignment tells you to plot 2 periods of a function, of a sine function with an amplitude of 2. All right, let's make it 2 so I don't have to mess up the board anymore. And a period of a period of 2 pi. I'm sorry, that would be pointless. A period of 2. What is omega if the period is 2? If omega is 2, then our period is pi. That means we're going to go to full max to full min and back to 0 from 0 to pi. So we know that at the origin we're going to be sine of anything is still 0, and we know at pi it's going to be 0, but we also know that now at half of its period, pi over 2, it's also going to be 0 here. We know at the full period, at 0, at the full period, and at half of its period, it's going to be at 0. And we know that at half, sorry about that, folks. At 1/4 and 3/4 of its period, it's going to be at +1 and -1 respectively. So we can now plot the first period of a function that has an amplitude of 2 and a period of 2. Or if we were writing it out, I'm sorry, that's not. What is omega when the period is 2? Pi. Sine equals pi x. Does everyone see how we did this? Let's try another one. Okay, what's our amplitude? We're plotting y is equal to 1/2 cosine 3x. Amplitude is 1/2. Omega is, and that means that the period tau is or 2/3 pi. That means for this cosine function, our period goes from here to here. Boom, boom. There's our midpoint and our fourth points. So we have points at x equals 0, pi over 6, pi over 3, pi over 6, and 2 pi over 3. This is going to be a little tiny one. And our amplitude is only going to be plus and minus 1/2. We're going to start, because it's a cosine function, we start at 1/2. We come to 0 at the quarter period. Go to -1 at half period. Back to 0 at 3/4 of a period. And back to 1/2 at the full period. There's one period of our cosine function. These are the key points that they're talking about. The period, the whole period, the half period, and the quarter period marks. Do we have any questions? What about homework assignment? Does anyone have any questions from your homework assignment? $49? Now, this is in what chapter? Okay. Okay, but let's look at what they're asking. They're saying in problems 43 through 58, find the exact value of each of the remaining trigonometric functions of theta. And let's see, 49, cosine theta equals minus 1/3. Pi over 2 is less than theta is less than pi. Okay, what does that tell us? Here's our unit circle. We know that cosine theta is minus 1/3, so that's here. And we know that pi over 2 is less than theta. And theta is less than pi. That means theta is somewhere in quadrant 2. Yeah, that's supposed to be a Roman numeral 2. All right, well, we know that cosine theta, we know, first of all, that this is our point. So we're looking for a positive value of sine. And we know that cosine theta is minus 1/3. How do we find the value of sine? We know the radius is 1 because it's the unit circle. So, anybody? Pythagorean's theorem. We know that 1 squared is 1 is equal to minus 1/3 squared plus y squared. What's minus 1/3 squared? Just 1/9. That's close enough. 1/9 plus y squared. So now if we subtract 1/9 from both sides, we get y squared is equal to 1 minus 1/9, which is 8/9. So y becomes the square root of 8/9, or the square root of 8 divided by the square root of 9, which is 3. And the square root of 8, can that be simplified any? So we know that our coordinates of this point P is minus 1/3 and 2 times the square root of 2 over 3. That means we now have the first two functions. We have the exact value of cosine and the exact value of sine theta. So what would then What's the next function? What are the other functions we're going to have to get the value for? We need tangent theta, secant theta, cosecant theta, and cotangent theta. What's the tangent theta? Y over x. Y is 2 times the square root of 2 over 3 divided by negative 1/3. That gives us minus 3 over 1 times 2 times the square root of 2 over 3. So it becomes negative 2 times the square root of 2. What's the exact value of secant theta? How do we find that? Reciprocal of cosine. Cosine is negative 1/3. The reciprocal then is just negative 3. Cosecant? Reciprocal of sine is anybody? All right, and cotangent? Cotangent minus 1 over 2 times the square root of 2. Once you have the cosine and you can find the sine, then the rest you can just pretty much write down by looking at what you've got. Biggest trouble you're going to have working problems like this is remembering that when they ask for exact values, square root of 2 is the exact value. You don't need to round it off in your calculator.
Question. I'm still looking on 44, for instance. We're dealing with fifths, but you can I'm just talking about simplification, like right here. The answer is negative 4/5, but it can be simplified to 2 over the square root of 5. I mean,
Well, no, not if what you've got here is right.
well, that's why it depends on how you're working the formula. If I got to.
What is this? This is 44? Okay, first let's I'm going to get this straightened out. Anthony Lee. That you? No. Okay. I take it some of you signed both of these? Oh, okay. Has anybody not signed in? Sign one of the roll sheets. Okay. As long as we're good. All right, we're looking at 44? Okay. We got cosine of theta is equal to what? 3/5, and we're in quadrant 4, which means sine will be negative, right? Okay. Before I go too far down the road, show me again what it is you're asking about.
Well, I'm asking because in order to work the formula, you need your denominator. It just need to match in order to work it. But after you get the answer figure, you actually simplify down to, you could by taking the square root of this, make it 2 over the square root of 5. I'm asking how far you want to take simplification.
Well,
you want it just to match across the answer.
I'm not sure why you would take the square root of that.
Well, I don't either. That's why I was asking.
Yeah, I don't know. I don't know why you did. But let's look at how this problem would be worked. Same procedure as last time. Where do we start? 1 is equal to 3/5 squared plus y squared equals 9 over 25 plus y squared. 1 minus 9 over 25 is equal to y squared. What's 1 minus 9 25ths? Or stated differently, what's not 25 minus 9? 16 25ths. Now we take the square root of this, both sides of this, and we get 4/5. But we know that we're in quadrant 4, so y then needs to be negative 4/5. Our sign becomes negative 4/5. Now what's the tangent? Negative 4/3, exactly. This divided by that, the 5's cancel and we're left with negative 4/3. Secant. Five over 3, cosecant. Negative 5 over 4, and cotangent. Bada bing, bada boom, we're done. That's it. This is the only time you would have taken a square root.
Right. Well, that's what I'm asking. Is because some of the formula you have to take the square root in order to figure the formula. So I was wondering if you want to, when you get the answer, even though that's the answer that I came up with, if you want to go to the square root.
Well,
some of the formulas up here, you have to find the square root in order to work out the equation.
You needed to take the square root when you're solving the Pythagorean's theorem to get the
question correctly. Okay, if we start out with an equation, okay, so then if we take this 38, it starts out with square root of 5 over 5.
Oh,
in order to figure the equation, you have to use the square root of 5 in order to do your fractions correctly. That's why I'm saying how far. I'm talking about simplification thing now.
you're talking about simplification. This is a good question he's asking because this is a lot of you in the engineering sciences are going to run into this. When you have something like the square root of 5 over 5, is that as simple as you can make it? Well, say again? No, the square root of 5 over 5. That's actually equal to the square root of 5 divided by the square root of 5 times the square root of 5, which means it can cancel. It can actually reduce to 1 over the square root of 5. Okay? I'm going to recognize either one of those.
That was my question.
Yeah. Okay. I'm going to recognize either one of those. Which one is the more simple? It depends on whether you're an engineering student or a nursing major. It's that's at that point it's down to preference. So you get it down to either one of these forms, and I'm going to recognize it. Now, if you get it down to something that involves, 13 pi over the square root of e, then we're going to have problems. But you get it down to one of those and we're good. Is anyone else having any?
One just marker up there
Yeah?
on the top where it says 1 equals 3/5 squared. Where did the 1 and the 3/5 squared and all that stuff come from?
Pythagorean's theorem.
Okay, then where did the 3/5 squared? Where did you get that?
Because the cosine is 3/5. That was given in the problem.
Okay.
And that's your x coordinate.
Okay.
So x squared plus y squared is equal to the radius squared, which in this case is 1. 1 squared is still 1. But, and this is a good question to raise, what if this was a function that was not on the unit circle? What if they were asking you about what if they were asking you to find all of the functions of all of the trigonometric functions where the terminal radius includes the terminal angle ray includes the point, the x coordinate minus 2. Well, no, but you know that, and they would have to then give you a radius greater. The point is, there were some of these kinds of problems in the homework, wasn't there? Where the, say again? No, that's, let me find one here, an example of this. Because sometimes they may give you a point that's not on the unit circle. At that point, you've got to determine a radius. Here we go. Here's a good one. Example 12 on page 125, which going a little further back in the chapter. But here they ask you to find all of the exact trigonometric functions of the angle theta if the point (4 minus 3) is on the terminal radius. Is on the terminal ray of the angle. First thing you got to know is whether that point is on the unit circle. Well, we start with 4 squared plus 3 squared equals r squared. So 16 plus 9 equals r squared. 16 plus 9 is what, 25? So r is equal to 5, not 1. It is not on the unit circle. But we now know that we can scale all of the the trigonometric functions with the scalar of 5, a scalar coefficient of 5. Or we can just go back to the original definitions of the angles. What are the definitions of the angles? Well, the sine of the angle is the opposite divided by the hypotenuse. So we can write 3/5 is the sine of our angle, only it's negative. So it's actually -3 divided by 5 is the sine of our angle. I want to make sure you understand this, what's going on here. We're saying sine of theta is equal to -3/5. That means we're saying 5 times the sine of theta is equal to -3, which is our y-coordinate. We get from the definition of the angle, we can just multiply both sides of the equation by 5 to get the same result. And that's how we can see that hypotenuse, the radius of the circle that the point is on, is the scalar coefficient that increases what property of the function if we were plotting this function? Amplitude, exactly. That radius becomes the amplitude coefficient of the function. You see what? In other words, the amplitude, when we're going back to the beginning of this class, when we talked about plotting the graph of the sine of x, the amplitude coefficient is basically increasing the radius of the circle that all of those points will fall on. Okay? If we wanted to finish this problem, what's the cosine of this angle? The adjacent divided by the hypotenuse. Tangent, -3/4. Cosecant, -5/3, secant, and cotangent. Bada bing, bada boom, that quick. Are y'all starting to see the relationship between the amplitude coefficient, the amplitude of the function, and the radius of the circle that all of the points would fall on? Collars and cuffs. It doesn't really, honestly, it doesn't matter where you start. It's going to be confusing until it all starts to come together. Does somebody else, sure, is everyone here ready to ace the next exam? Or is everybody here ready to zip through this week's homework? Then let's go back. Well, first let me ask, does anyone have any questions about anything we've covered so far? Well, then let's do another example of graphing one of the sine or cosine function. All right, well, here's an example right out of the book. Let's graph the function y equals 2 sine negative pi over 2x using key points. Y of x is equal to 2 sine minus pi over 2 x. And we're going to use key points. First, what's our amplitude? Okay, what is our period? No, trick question. We'll keep going. We'll get there, right? Tau, the period is 2 pi divided by the angular frequency omega. 2 pi over omega. In this case, omega is negative pi over 2. There you go. You're right. Omega is negative pi over 2. The period now is 4. Sorry about that. What are the key points? We got 5 of them. 0. What's our function? Sine of negative pi over 2 times 0 is, sine of 0 is 0. What's our next key point? Well, we know that at 1/4 of tau, which is right here, sine is going to be what? Well, if the period is 4, then 1/4 of tau is 1, so we've got sine of negative pi over 2 times 1 is negative pi over 2. Sine at pi over 2 is 1. Sine at negative pi over 2 is negative 1. If we weren't doing that, if we weren't plugging in the values, if we were just looking for the values at 0, at a quarter period, a half period, 3/4 of a period, and 1 period, the values would be 0, 1, 0, -1, and 0. The key points. Good question. When we were plotting just the function of sine of x, sine of 0, at this point, the period of sine of x is 2 pi, right? Amplitude is 1. This period is 2 pi. Okay. You have period of 2 pi, pi, 3 pi over 2, and pi over 2. These are the 4 key points for plotting sine of x. They go from 0 to 1, back to 0, to -1, and back to 0. What's crucial here is to recognize that this is 1 period, 3/4 of the period, half of the period, 1/4 of the period, and then 0. That's right here. That's where you get your key points. Once you know your period, you take the whole period, half of the period, and then the two quarter points. And you know at 0, sine is 0. At 1/4 of the period, which in the case of the period of 2 pi, this would be pi over 2, but in general, it's 1/4 of the period. The value is 1. At half the period, it's back to 0. At 3/4 of a period, it's down to -1. And then at the full period, it's back to 0. But here's, everybody perk up and pay attention. Get your note writing pen ready, because I'm fixing to give you a tip that's going to stop you from getting tricked into writing a wrong answer on your homework. We're doing the sine of a negative value here, a negative angle. Because our amplitude, our omega is negative pi over, our angular frequency, our angle, theta, is a negative number. Sine is an odd function, which means that the sine of minus theta is equal to minus the sine of theta. Cosine is an even function. So the cosine of a negative function, of a negative angle, would be equal to the cosine of the positive angle. Sine is odd. So if we have a sine of a negative angle, then we get negative the sine of that angle. Which means here, we would then change this to 0, -1, 0, negative of a negative is a positive, and back to 0. So when we're plotting this function on this graph, we've got our key points now. 0 is 0, 1 is -1, half period is 0 again, 3/4 of the period is now +1, and back to 0. And now we can plot the graph. And of course, once you've plotted the first period, if they ask for 2 or 3 periods, you can just extend it. Yes, it was. And I overlooked that. Good catch. That means this point would actually come down to here. This point would actually go up to here. These 3 points are 0, so 2 times 0 stays 0. And that means the proper graph would look like that. And he would have gotten the points, and I would have lost points on the homework. Anybody else have any questions? If you're plotting a function, the general form of the function is going to be amplitude times sine omega x, or amplitude cosine of omega x. And from those numbers, you can calculate your period and your key points. Key points are 0, the whole period, the half period, and the 2 quarter point period in the period. Or 0, period, a quarter period, a half period, 3/4 of a period, and the whole period. Be certain to check whether it's an odd or an even function when you start plugging in these numbers. And don't, as I just did, forget to multiply to scale by your amplitudes. Sure.
You want those things together?
Is it 1 or 2 assignments?
Both of them. Both sides.
It's 2 separate assignments?
Yeah.
Yeah, then no. No, I'll keep them. I'll keep them separate. That way I can grade them separate.
Can I have the one that had the name on it?
You bet. Is it yours?
It could be. Yeah, that's fine.
Okay, could you write your name on it and I'll give you the grade? Thank you.
Are you got them? You're still in the same pile?
Yeah. Thank you.
On that assignment thing,
Uh-huh.
I went in there and it doesn't, I thought I saw one with deployed over the submit button, but it's not. What I'm saying is, you go set up a new assignment for that, called test or something for that one. And when you set it up, you go down there and you see at the bottom of the description, there's a box there that says everybody.
Okay.
If you change that box and just put my name in, I'll be the only one who sees it and can connect to it.
Uh-huh.
Then I can upload that assignment and you can practice, or you can see what I was talking about grading it online.
Okay. Well, I'll have to, I don't, honestly, I'm not sure if I'm going to have a whole lot of time to experiment with that sort of thing right now. I just found the bug in my, I can't say it's a bug, it's one of those hidden little check boxes that's like 3 pages deep in a sub-menu off of a sub-menu, but I just found the checkbox to get my online classes. to upload their grades from Pearson to Canvas.
Oh, yeah.
Only now I have to go through every section of the class and go through every assignment on every section and change and dig down into the menus and change that setting and save and reassign it. So
Because you did all the work before you checked.
if I do, well, I didn't, no one knew. No one knew to do it. It wasn't, you know, it was.
I've done that on stuff, and then you're like, oh,
Hey, you.
shoot, do what you're doing.
Well, yeah, I mean, this is one of those things where the people who've been doing this course, and this isn't new, this isn't unique to Canvas, this is going all the way back to Brightspace. The people that have been teaching these online classes for semesters now
Didn't know.
didn't know to set it, and that's why, you know, when I asked them how did they do it, it was like, oh, well, I just have to go in and manually shift them. Well, okay, that's not good.
No, it takes too much time.
So yeah,
See you Thursday.
take care, Val.
You go on Friday?